Okay, so in the last class we discussed about color image processing. So we basically discussed two models, two color model. One is RGB and another one is HSI. So what is HSI stands for? Hue, saturation and intensity. So how is hue obtained from RGB values? So the angle with the reference color point, which is the red that is being taken. What is saturation? How is saturation obtained? In distance from the black and white intensity axis. And how is the intensity value obtained? Intensity value. If you know a color with a given RGB component, let us say, how do you get the intensity component? That is for intensity or that is for saturation? Saturation is full at the boundary and 0 at the black and white grayscale intensity value. Intensity value, as from the model we discussed that the plane containing that color point or the color vector, if you draw a perpendicular plane and the point where it intersects the intensity axis, that value will be the intensity value. So we have formulas for that, but so today we will discuss this some of the applications, or how do we process color images and what are some applications in computer vision. One thing in the last class somebody pointed out that, so I just verified it, that whether the human eye is more sensitive to the red or the green color, because in the introductory class I had shown that there are twice as many green filters in the colors camera. So the reason the reason is slightly different why they are twice there. It's not because the number of percentage of roads which are sensitive to red light are maximum. So the yesterday's data was correct, what we said, but green filters are helpful in the sense green filters actually pass most of the amount of the intensity. So most of the energy photons are passed. So in terms of the quality of the image, using more green filters helps in improving the resolution and the quality of image, because the intensity, the signal value is higher if we are using green filters. So green filters basically pass to, more amount of more energy, more amount of light energy than other filters, than the other two filters. So that is the reason why they are used more in color cameras. So I just verified whether both the statements are right or not. So one of the simplest use of color can be in generating a pseudo color map. So given a grayscale image, we may generate a pseudo color image by assigning different colors to different level of intensity values. And the motivation for doing that we showed in the beginning slide. If there are more, human vision can, because when we introduce colors, the number of shades are more than the number of levels of intensity images, and human vision can discern more details in a color image than in a black and white image. So generating a pseudo color image is helpful for visualization purpose. So to generate a pseudo color image, we can do a simple operations. One of the simple operations can be like doing kind of a intensity slicing. So if you recall, we have already discussed intensity slicing. So for example, if we So let us say we have a grayscale image with intensity values from 0 to maximum level L minus 1. So if you want to let us say give two colors to this image, we can just slice this intensity axis, divide this into two levels. One is this and another is, so all the intensity values in this thing can be given one color, and all the intensity values in this range can be given a second color. So this can be a simplest way of introducing color. So this is an alternative representation of the intensity slicing. So all these intensity values are given color 1, and the other remaining intensity values are given color 2, and we can extend it to multiple colors C1, C2, C3, C4 and so on. So an example of this is shown here. So this is a monochrome image from some biomedical X-ray or radiation patterns. So of course this is also not exactly grayscale here, but it doesn't has many shades of colors. So we can actually introduce pseudo colors by doing those intensity slicing. So different levels of intensity values, we can give different color, and we can get this kind of a pseudo color image. And as you can see, this probably may be more informative for a doctor to see the different parts. I don't know what this structure is all about, but maybe the another image can help you. So this image, I think many of us see in weather news. So normally we have this kind of a pseudo color image. So this is an example of a rainfall statistics taken from some instrument, and this is basically a grayscale image which is measuring. So low value means low rainfall there in that region, and high values of the intensity means high rainfall. So this grayscale value gives some idea, but if you introduce pseudo colors, different pseudo colors here, as you can see, different intensity values being given different shades of colors, then we get this kind of a pseudo color map. And probably looking at this image, it's more easy to figure out which are high concentration rainfall area and which are low concentration rainfall area than looking at this image. Will be more able to discern. So these are just a zoomed in portion of this image. We can see these are the highest concentration of rainfall areas, whereas these are the low areas. So this is one way to generate a pseudo color map. There are other methods to generate pseudo color, not simply. These are simple intensity slicing, but there are some more complicated functions can be used to generate a pseudo color map. But this is just one simple example of a doing intensity slicing in color space for better visualization. We can also do other low level processing that we did for grayscale, like smoothing operation or intensity transformations, histogram equalizations. All those things which we did on grayscale value can also be extended for color images. So so let us see how they will be extended. So the only difference now in a color image, now we have a vector for each pixel rather than a single scalar value. In grayscale image we had just a single scalar value. Now if you are using an RGB color model, we have 3 components. Even if you are using HSI model, we have at least 3 components for each pixel. So we have a kind of a vector in for every pixel in the color space. So the transformation that we may be doing in color image, either we can take each component separately and do the required transformation on each component separately, or take the entire vector and do the transformation on the vector itself. So either do a scalar transformation on each component, So either do a scalar transformation on each color component, or take the RGB vector itself and do a vector transformation on the things. Most of the time we'll see that doing either way will result in the same result, because most of the time both way these are equivalent methods, because it depends on the transformation that you are doing. For example, if you are doing a simple averaging operation, so doing an averaging operation on each component separately and doing an averaging operation on a vector, both will give a same result. So that depends on the operation that you are performing. So let us see some example. So for example, let us say we want to do some transformation, some color transformation. So when we were doing an intensity transformation, we use a transformation function. We took the intensity value and applied a transformation function to get the new intensity value. In case of color, now because now we have a scalar here, we have multiple components for each color. So those components are represented as R1, R2, Rn. So normally there are 3, but there are some other color spaces, color models which have more than 3 components, which have 4 components and so on. So in general we are just denoting it by some n component vector. So you can have a transformation function which will apply on each component separately. So for example, you can have a transformation function T1 which will take all these. So in this case, so here what we are showing is that now this transformation function T1 is taking each color component and then generating the first component S1 in the output. The second transformation T2 is taking each color component and generating the second color component in the output, and so on. So this is this kind of a this in this case now the result by doing it's taking the entire vector and doing a vector based processing. So this is an example of doing a vector based processing. We are taking the entire component and then doing a applying some transformation on it to get the corresponding component in the output color image. Very rarely this is done, but you may need this kind of a transformation. This will result in change in the color itself, because when you're modifying the colors, when you're taking more than one component and modifying some transformation, then your colors and everything will change, so your image may look totally different. Normally, if you want to do a color transformation, it may be better to first transform into an HSI space rather than using a RGB space. The advantage of using HSI space is that it decouples the color information from the intensity value. So if you want to only change the intensity, just change the intensity vector, intensity component, or if you want to change the color or saturation, you just separately change the color and saturation. So some operations doing color transformation may be easier in doing an HSI space rather than in RGB space. So a simple example, let us say we just want to modify the intensity value, not the color, just want to modify the either make it brighter or darker. So if we are using an HSI color space, we can just take the third component, which is the intensity component, and apply a simple scalar value, scalar factor, and get the output component, which is the I dash, and we don't change the H and S value. So this seems simple, but remember, going from RGB to HSI space may require some operations. So some computation is needed to go from RGB to HSI and back from HSI to RGB. In case of if you want to do the same thing in RGB space, then you have to multiply every component by same scalar factor k. So if you scale each component by the same scale factor k, your intensity value will get scaled by same factor. An example of doing this in an image is shown here. So we have a full color image. So the three components in RGB space is shown here, and in HSI space is shown here. The hue component, the saturation, and the intensity value, and the red, green, and blue. You can see these, most of the strawberries are red, so these values are higher values in the red component. Similarly, so can you explain the hue component here? This red, why they are not black here? Why they are brighter? Because there was a problem with hue. We said hue is discontinuous. So if it is slightly above, if it's slightly low, it can have either black or totally white. So it may be slightly on this side of the red spectrum rather than on the that side of the red spectrum. Green of the it's not exactly black, it's some grayscale value. It's not coming here, it's some intermediate grayscale value. So green is at 120 degree or 60 degree. So 60 as compared to 360, it's towards the darker side. But what we want to show, that we want to change the intensity value. Let us say we want to scale it by some factor k. K here is I think less than 1, so it will decrease the intensity value. So in RGB space, you have to, as I said, we have to, each component, each RG and B component has to be scaled by the factor of k. Whereas in HSI space, you don't change, H and S remains the same identity. Only the I component is scaled by k. Both will give the same result. So the output image will be this, whether you do this way or this way. So in this case, probably doing it in RGB space will be more easier rather than computing from RGB to HSI and then going back. Here probably if you just want to change the intensity value, it may be easier to do in RGB. But if you want to change the hue or saturation or something specifically, then better go to HSI model and then do the transformation. Let us say you want to do the histogram equalization, then it would be better to go into HSI space, take only the intensity component and do the equalization on the intensity component. So the same thing is shown here, H and S remains the same. We generate the histogram of the intensity component and do the equalization there, and this is the result of the image. So there is some details which is being shown here, which is better as compared to the original image. It's not quite a good, I don't know if it is visible here or not, but at least you can see here some more details have become visible after doing the equalization operation. So these are simple methods to extend the same thing that we were doing in grayscale image on the color. Similarly, if you want to do a special filtering operation, like doing taking a special mask and doing either averaging operation or sharpening, smoothing, whatever, then also we can, for example, if you are doing an averaging operation, so that depends on the operation that you are doing. So if you are doing an averaging operation, take the color vector and take that neighborhood around that pixel. In that neighborhood, you are basically doing an averaging operation. So this equation is showing a vector processing. But if you because this averaging operation, because of the property of this averaging operation, it's same as If you do take the each component separately and do then averaging, both are equivalent. Both will give the same output color vector, whether you do per component processing or you take the vector and average the vector, do an averaging on the vector itself. The result, an example of doing a smoothing on this image is shown, will be shown in the next slide. So this is an original image. It's R component, green RGB component. I think this will be B, and the HSI component shown here. So after smoothing by a 5x5 filter, in HSI space you will have to do smoothing only in the intensity value. You won't do the smoothing in the hue and saturation. In HSI space you will do the smoothing only on the intensity component, whereas if you are doing in RGB space, we will have to do smoothing in all the three components. And the result of doing those is shown here. Here there will be slight difference if you are doing smoothing only the intensity component of HSI model, whereas if you are smoothing the RGB model, if you subtract the two results, you can see there is some difference here. Why is the difference? Because when you are doing an averaging operation on the RGB space, your color may get modified, because now you are taking an average of the neighborhood of the color. So your resultant color may be slightly different color than the original color which was there. Whereas in HSI, because the color information is decoupled, if you are doing an averaging only on the intensity value, the color will remain unchanged. The hue and the saturation value will remain unchanged. In this image, it doesn't see much difference here. Probably if you increase the size, you may get some difference in the color. But you will find some difference, and which is shown here. If you take the difference here, you are seeing some quantitatively some differences there in the result of both. You may also want to extract in a given image, you may want to extract regions of a particular color. You may want to segment it out, or you may want to highlight a particular color region. So you can do some kind of thing what is called color slicing. Doing this, if you remember, we did gray level slicing when we discussed intensity grayscale images. So in gray level slicing, you can suppress all other intensity values and only highlight only a range of intensity value by taking this transformation function. This transformation function is basically highlighting only intensity values between A and B and suppressing all other intensity values to a low value, or you may leave them unchanged and only emphasize the particular intensity value between A and B. If you have to do it same in the color, now because you don't have only a two-dimensional space, you have a three-dimensional space. So how do you select a region of interest for highlighting or for extracting or slicing a particular color? You will have to select a particular region around that color. Now you may select that region, you may select a spherical region around that color. So this is the reference color, let us say. You may either select a spherical region around that color, or we can select a cube around that color. How we specify the region around that, it is our choice. We can specify a cube around that, or we can specify a sphere around that. Accordingly, our equation will change. So what this is saying, if we are specifying it by a cube, so what we want to do for a particular color point, we want to highlight all the colors in this region and suppress the remaining colors in a given image. So what we are doing is that, so let us say the specified color is represented by a1 comma, let us say this is our specified color point. So we take the distance from that color point in each component, in each dimension. If that distance is greater than the size of the square, so size of the cube, so if it is greater than half of the size of this cube, so because this is in the center, so this is size is w by 2. So if a given color is falling outside that cube, we'll make it some neutral color. So some arbitrary value you can give it, you fix it to some neutral color, and you leave the otherwise if it is inside that region of interest, you leave it unchanged. So you are basically masking out all other colors and you are only leaving the color of interest, the region of interest unchanged. If you are specifying our region of interest by a sphere, we'll have to use this equation. So this equation is basically taking the radius from that center point. If that radius is greater than the radius of the sphere, so it is taking equidistant distance here. If that equidistant distance is greater than the radius of the sphere, then we are suppressing it to a neutral color point. Otherwise, we are remaining it, letting it unchanged. So example of doing this color slicing. So this we are doing when we are using an RGB color space. So this thing, remember this is our RGB color model. If you are using HSI model, we'll have to do it slightly differently. So this is an example of doing a color slicing for this red image, for this red component. The reference color point is the color of the strawberry. So these are result whether you are specifying a cube as a region of interest or a sphere as a region of interest. Results are almost same. I think here we have slightly better output. We could have done this thing in HSI space. How? We could have just extracted the we should have taken only the hue component, because color, if you are only interested in particular color is only captured by the hue component. So we could have just used you could have just used simple gray level slicing on the hue component itself. But the problem is only with the red component you have to be careful. So this is why if you wanted to do this operation, it was better to do in RGB space, because hue space has a problem with the red things. So if you want to extract only red color, better to do it in RGB space rather than doing it in HSI space. All other colors better go into HSI space and you only do a gray level slicing on the hue component. It will be more easier to do. So simple application of this slicing, you can use it for segmenting a object of a uniform color or a almost uniform color in a almost uniform background. So this is an application where a robot is playing a soccer. So because the background on where the ball will be all green or white, and the soccer ball will be of particular color or a color within that region of interest. So you can easily do this color slicing to segment out this ball color from the remaining thing. We'll see segmentation in more detail, but this is the simplest way of doing a segmentation, color based segmentation of our object. If the background is, in this case the background and the object have a clear distinction, if the color is clearly distinctive, we can actually do this kind of little more advanced application of color in machine vision. We can use color information for as a descriptor for an image. and then matching it with other images in the database. So it is very frequently used for content based image retrieval. So given an image, you can try to retrieve images which are similarly looking in the database. So our Google search engine and many other search engines, they quite heavily use color for retrieving images from the web. So what you do basically in there, take the color image, take the distribution in each component, either in RGB or HSI, whatever model space you are doing. See that histogram. So you get 3 different histograms in each component. Now use this histograms itself as a descriptor for this image. Now the advantage of using histogram is as a descriptor is that it is a global descriptor. It is invariant to translation, rotation, scale. So if the image has been rotated or translated, the object has been translated, or scale factor has been changed, the histogram will not change so much. Scale it may change little bit, but with translation and rotation, the histogram remains unaffected. So these are some other examples of images. So as you can see, these two images have quite similar looking histogram. I don't know these are the actual representation or just for the, but as you can see, they have quite similar looking histogram distribution. So they may not be the exact histogram, it's just for depiction purpose, but it may be quite possible two different images with two different content may have a similar looking histogram, and that is one disadvantage is using a histogram, because histogram is a global descriptor as we said. So whether a particular thing is, so here for example in the background you have a lot of greenery here also you have a lot of greenery here. So it may happen that the red distribution, the green distribution here and the green distribution here may match, and similarly the black distribution here may match with the other black patterns in the thing here. So it is not so accurate thing. There are some other advanced things that are done to make it more accurate, but in a simple way, what we can do here, if we have a database of image, we can extract and store the color histograms for each image in our database, and when a query image is given, we can extract the histogram for color histogram for that query image also, and then do a matching. So we can use some histogram similarity measure. There are several of them. Many of them basically try to see how much the two histograms are matching, how much they try to calculate the overlapping area between the two histograms, and using that they basically try to find whether the two histograms are similar or not. So using the similarity score, you can then sort the things and then rank them based on the, so you can extract, okay, top 5 matches, the lowest or the highest score, the top 5 highest score can be the top 5 closest looking images to the query image. So an example of that, so let us say we have these images in our database. So if you are given this query image, then from these images in our database, using a histogram based matching, we can get these top 5 images as our best match, which looks reasonably okay, not quite accurate because these are mostly images of pandas here, but they are also in the forest area, and this is also a forest image. Similarly, this image will retrieve this closest looking matches will be this. So as you can expect, why? Because the color distribution in here is closest to the color distribution here, and these are little further away. So probably this is the best match, this is second best match, and so on. This one is giving this as the closest retrieve image. So these are further images of things. So you can see clearly that you may get some of the good matches here, but some of the matches may not be related to the query image, and that is possible because we are using only a global descriptor. You're not trying to match objects there, you're not trying to use features here. But these are simplest thing, but still, even if you are using this simplest method, still you can see some of the results are quite close. So at least you can get a baseline performance using this simple color histogram and doing simple matching of the histogram values itself. And then you can refine using more advanced, you can use shift features, you can use Harris features, do feature matching and do all those advanced things to further improve the result. But at least you can get some uh, baseline performance for that. Another important use of color in computer vision is for skin detection. Many times when you want to detect persons or faces in an image, skin is up, because skin of faces and other portion of the bodies, they may be easily detected using the hue of the skin. Generally it is found that the hue value of different skins of people in different parts of the world, they actually fall within the same segment, or almost around the same region. So you can basically segment out. uh, it may be a little surprising because there are black people and there are white people, uh, but I don't know, but they say that the skin pigment which gives the color to the skin color, because that is the same, I think melanin or whatever, that is same for everybody. So it has some common characteristics for each thing. So you can use the hue color to try to segment out skin portions from the images. So this one paper doing that. We will discuss this method more in more detail, but I'll just give you a basic idea how to segment out skin regions. You basically take some sample images in our database. You need to mark skin regions. Sorry, manually you need to mark skin regions and then generate a probability distribution. So given from these skin pixels, so use now you the feature that you will be using the hue value. So from these skin pixels, you can distribute these skin pixels in different bins of the hue. So you can use the hue as our histogram features and create a histogram of hue and generate this distribution. So this will give a probability of a particular feature value, or a particular hue value, provided it is coming from a skin region. So probability of a particular hue value to be a skin, uh, or no sorry, probability of a skin pixel to have a particular hue value will be can be easily modeled in that way. You have a database of images, training images, where you mark out skin regions and then distribute them in the bins, and from the histogram things you can generate this probability score, probability of a skin value having a particular hue region. It may not be the same, it may be some distribution. Similarly for the non-skin regions also you can generate the probability distribution using the histogram value, and then you can use the Bayes theorem. I'll go talk about this in more detail when we discuss high level image computer vision, but I'm just telling you a basic thing. Then you can use basically the Bayes theorem. So now let us say let us say this is A, this is B. Oh sorry, you can say this is B. So PB given A is known. So we can generate PA given B using the Bayes theorem. So we can generate, given a particular hue value, whether it is skin or not, you can model that class by so that's why it's called generative modeling. From these kinds of data values that we have from the database image, we can generate the model for skin class, and similarly we can generate the model for non-skin class. And so between these two values, the probability of a given hue having a skin is more than non-skin. So if our hue value is falling within this range, we will classify it as a skin portion. If it is not falling, if it is falling outside this skin, this region, we'll classify it as a non-skin region. So this is a basic idea of using color for detecting skin region in humans. So I'm just telling you some applications of colors. We'll see more applications when we discuss color-based segmentation after sessional. So these were some applications of using color in